All right, so hang on and watch for just a second because we're going to set this up just a little squirrely this time. So in just a moment, you're going to tape things in, not just yet, but in just a moment, you're going to take the vocab at the top so that we can't see the term or can't see the definitions, but we can see the terms. Then your little map goes down below, but we need the Post-its underneath it. So make sure that you tape it in so that we can get underneath and then put the two Post-its side by side. Okay? All right, go ahead, tape in vocab at the top, fold it over, tape in your map, but tape it in so we can see the two Post-its underneath. We will take it.
There wasn't one in my bag.
All right, we're going to start with our little Post-it notes. And off to the side, notice that I put ocean currents. This is going to have to do with ocean currents, and my little Post-it notes have to do with ocean currents. So I put it off to the side, so basically it applies to everything. Okay, two types of ocean currents that we are going to be looking at. The first one are our deep ocean currents. These are considered vertical currents. V-E-R-T-I-C-A-L, vertical. Deep ocean currents, and our ocean is very deep, kilometers worth of water. So these are vertical currents because essentially we're looking at how that water is being transferred from the surface down below, and there's I'll get to that in just a second. We'll get to the characteristics in just a second. All right, the other one, surface ocean currents. Surface currents are up there at the top, not the very top. They're just a little bit underneath the surface, but they're up there at the top. And they help to distribute heat. Surface ocean currents help to distribute heat. So yesterday you were looking at deep ocean currents, the little NASA Go with the Flow activity. Do you remember what characteristics you had to mess around with to get to the little end of the maze? Heat, temperature, and salt. So heat and salinities. So whether it be hot or cold. When we talk about heat, what was the word part that we had before when we looked at the layers of the atmosphere? And we used the long glass tube thing. What word part means heat or temperature? The thermosphere was the layer of the atmosphere, and we said thermo when we were talking about heat. So thermohaline, haline. So that's indicating both the temperature and the salinity and how those characteristics are together moving these currents in the ocean. So underneath deep ocean currents, underneath that Post-it note, you are going to put the fact that deep ocean currents are driven by thermohaline circulation. Thermohaline circulation. Thermo indicates the temperature. Haline indicates salt or salinity. Deep ocean currents are driven by thermohaline circulation. Thermo indicates the temperature. Haline indicates the salt or salinity. Okay, so your little boat, or submarine, I guess it was. What did the temperature part do? Do you know why it made the little submarine go up? Heat rises. Convection currents, that's the red arrow that we draw up. So in any kind of fluid, and water obviously is a fluid, hot water is going to rise. So it's going to be up there on the surface. I don't know if you've ever had the experience, so in May, when it's just starting to warm up, and we might have had like 1 week of 80s and 90s, and you're like, oh, I want to get in the pool so bad, just really wanting to go swimming. You get in the pool, and the very top layer, little thin layer, is warm, but underneath it's still freezing cold. The water hasn't circulated in the stuff at the top. The hot water, it's right there where the sun's hitting it anyway, and so it's going to stay there at the hot top because hot materials rise. All right, submarine, what did the salt water, what did the saline, what did the salt do to it? Do you know why? Density, heavy. So if you take water and add stuff to it and we dissolve that stuff into it, we're making it more dense. I can do that with sugar. And in fact, I do that in the biomed lab to create sample DNA samples so that we can load wells. And so it sinks into the well instead of floating around into the gel electrophoresis chamber. You add stuff to it, you increase the density. It's the same amount of space, but there's more stuff in that space, so it makes it heavy, so it makes it more dense. All right, so deep ocean currents. Underneath surface ocean currents are driven by wind and tides and is shaped by land masses and the Coriolis effect. Surface ocean currents are driven by wind and tides and is shaped by land masses and the Coriolis effect. Surface currents are driven by wind and tides, and they're shaped by land masses and the Coriolis effect. Surface currents are driven by wind and tides, and they're shaped by land masses and the Coriolis effect. Surface currents driven by wind and tides, and are shaped by land masses and the Coriolis effect. Little post-it notes go on top of that. And the little diagram goes on top of that. Okay, so let's take a look. I showed you the little winds in the atmosphere yesterday. So let's take a look at how things are different today, because our little hurricane, hey, that's not what I want. There we go. It was down here a little bit further yesterday. Now he's right about here. They're expecting it to make landfall, I think, 1 o'clock in the morning tomorrow. So everybody I know on Florida's west coast is kind of battening down. But these are showing winds. This is winds in the atmosphere. Okay? Surface currents, deep ocean currents, which one's affected by winds? The surface currents are affected by winds. So when I look at surface currents, which is what this guy is, these things are affected by winds. When I look back, oh, and in fact, I can even look at, I forgot I had, so this is wave action. This will even give us a better idea of what's going on. These are waves. This is the very top of the ocean water, and these are waves. Swish, 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 waves. So this gives us an even better look at how winds are affecting the surface of the ocean, because this is a really obvious place right here. So we've got all of these winds moving in different directions. Take a look at the direction of the waves. You can even see that boundary right there where things are changing. Down here where the hurricane is at, notice that the waves are essentially moving out from that hurricane, which is how it works. I mean, where that hurricane's at is a huge low pressure, so it's pushing everything out. And those winds, wherever the center of the hurricane is, the winds are moving out of where that hurricane is at. So we can visibly see on the wave action where that hurricane's at by the fact that all of these winds are moving out. So back to so these currents are a little bit under the surface. So they're down a few meters, 30 meters, 50 meters. Oh, I have to go back and look. I can't even remember. And it doesn't tell me on there. So these are down underneath the surface a little bit. But one of the characteristics are the fact that those surface currents help to distribute heat. So here's the equator, very red, very hot. North Pole, very blue, very cold. But look at how these currents bring that heat up and help to bring the cold down and help to mix that and regulate those temperatures in these areas. So these surface currents are helping to move around and regulate temperature. These surface currents are also affected by land masses. So we can see that all of these land masses are affecting the direction of those currents. So it hits land, it swirls it around, hits land, it swirls it around. There's a better place, but I can't remember what I was looking at before. Hits land, swirls it around. Remember when we were talking about tectonic plates before? So this guy's moving up this way. These guys were moving apart. So Horn of Africa, this is that area where I was talking about. This is getting a bigger and bigger area of water because those plates are separating, and it's separating where that continental crust is at. So this is getting bigger over here. Just thought that was interesting. All right, so those are our surface currents. I have yet to find a really cool video for my deep ocean currents. So we're just going to go ahead and label our diagram. What do the red arrows mean? Yep, hot, warm, heat. What do the blue arrows mean? Cold. So this is a very generalized idea of what's happening way down deep in the ocean. Go ahead. I don't think we have an equator drawn on ours, do we? Make sure you draw an equator, because notice how these currents turn differently in the northern hemisphere than they do in the southern hemisphere. In the northern hemisphere, they're moving clockwise. In the southern hemisphere, they're moving counterclockwise. Our convection currents are moving in different directions. Forgot to hit record. So yes, salinity, concentration of all the dissolved salts in the ocean. And when we think of salt water, when we think of sodium chloride, like table salt, but it doesn't have to necessarily be that. There's like magnesium salts and calcium, and there's other stuff that's dissolved in there as well. So all of that is incorporated into it and adding to the density. On the outside of your vocab sheet, please add that heat makes water less dense so it rises. Salt makes water more dense so it sinks. And then notice that I highlighted salinity in green and I only underlined the salinity portion of that statement. Heat makes water less dense, so it rises. Salt makes water more dense, so it sinks. I highlighted salinity, and I only underlined with my highlighter the portion of that that pertains to salinity. All right, so short little video talks about ocean currents. Don't even add. Oops. Oops, hang on. I know I turned the volume down on that.
In 1992,
there you
a
go.
cargo ship carrying bath toys got caught in a storm. Shipping containers washed overboard, and the waves swept 28,000 rubber ducks and other toys into the North Pacific. But they didn't stick together. Quite the opposite. The ducks have since washed up all over the world, and researchers have used their paths to chart a better understanding of ocean currents. Ocean currents are driven by a range of sources: the wind, tides, changes in water density, and the rotation of the earth. The topography of the ocean floor and the shoreline modifies those motions, causing currents to speed up, slow down, or change direction. Ocean currents fall into two main categories: surface currents and deep ocean currents. Surface currents control the motion of the top 10% of the ocean's water, while deep ocean currents mobilize the other 90%. Though they have different causes, surface and deep ocean currents influence each other in an intricate dance that keeps the entire ocean moving. Near the shore, surface currents are driven by both the wind and tides, which draw water back and forth as the water level falls and rises. Meanwhile, in the open ocean, wind is the major force behind surface currents. As wind blows over the ocean, it drags the top layers of water along with it. That moving water pulls on the layers underneath, and those pull on the ones beneath them. In fact, water as deep as 400 meters is still affected by the wind at the ocean surface. If you zoom out to look at the patterns of surface currents all over the Earth, you'll see that they form big loops called gyres, which travel clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. That's because of the way the Earth's rotation affects the wind patterns that give rise to these currents. If the Earth didn't rotate, air and water would simply move back and forth between low pressure at the equator and high pressure at the poles. But as the Earth spins, air moving from the equator to the North Pole is deflected eastward, and air moving back down is deflected westward. The mirror image happens in the southern hemisphere, so that the major streams of wind form loop-like patterns around the ocean basins. This is called the Coriolis effect. The winds push the ocean beneath them into the same rotating gyres, and because water holds onto heat more effectively than air, these currents help redistribute warmth around the globe. Unlike surface currents, deep ocean currents are driven primarily by changes in the density of seawater. As water moves towards the North Pole, it gets colder. It also has a higher concentration of salt because the ice crystals that form trap water while leaving salt behind. This cold, salty water is more dense, so it sinks, and warmer surface water takes its place, setting up a vertical current called thermohaline circulation. Thermohaline circulation of deep water and wind-driven surface currents combine to form a winding loop called the global conveyor belt. As water moves from the depths of the ocean to the surface, it carries nutrients that nourish the microorganisms which form the base of many ocean food chains. The global conveyor belt is the longest current in the world, snaking all around the globe, but it only moves a few centimeters per second. It could take a drop of water 1,000 years to make the full trip. However, rising sea temperatures are causing the conveyor belt to seemingly slow down. Models show this causing havoc with weather systems on both sides of the Atlantic, and no one knows what would happen if it continues to slow or if it stopped altogether. The only way we'll be able to forecast correctly and prepare accordingly will be to continue to study currents and the powerful forces that shape them.